Hello, students. Welcome in to week 11. After tonight's class, there will only be 5 more classes remaining. That's pretty darn good. But also, if you have not been keeping up with ck12.org, it might not be such exciting news. Please keep up on that. Remember, that is pretty much all of the classwork we're doing is on there. The adaptive practice and the quizzes. It's like classwork and quizzes and tests. If we were meeting in the classroom, that's what I'd be doing. I'd be giving you classwork. We'd be taking quizzes and tests. We're not in the classroom, so you got CK12 work with quizzes. So don't get behind on that. If you're having issues, let me know. We can work through individual problems. And if we do that, I can always go back and change the scores. So I have that power. I am godlike in that sense. I'm joking. I'm not godlike, but I do have that power. So just communicate with me. I don't want you to struggle. I don't want you to worry about your grade. Just email me, message me, whatever you need to do. But don't let that be the reason we don't pass a class. Because even if you suck on the CK12 stuff, we'll work through it together. That's what they pay me for. So make me earn my money, please. Anywho, so week 11. So last week, all we did was have extra time to work on the week 9 stuff. The week 9 stuff was talking about motion, velocity, speed, acceleration, and those were very important primers as we move into this week, which is Newton's laws of motion. And it's one of my favorite units. I take it very seriously because Sir Isaac Newton is one of my personal heroes. Just a phenomenal scientist, an incredible human being that was spookily connected to the universe. So you figure he came up with his laws of motion, he came up with laws of optics, and he discovered calculus all before he was 26. Before I was 26, the most I ever did was eat an entire box of Lucky Charms in one day. And I still do that, so I don't know. There's something beside for consistency there. Let me stop wasting your time and hop into the unit. So here we go. So here's our familiar. I'm so sorry for all of you. Here's our familiar dashboard page for Canvas. So physical science, let's click into it. You're going to see the stuff you've always seen, except the list has grown progressively longer. At the very bottom, follow this link to week 11 module. So we are in week 11, so just click on that and it takes you to literally everything you have to do for the week is contained right here. So the first one, Newton's laws of motion discussion board. This is all, it should be very familiar to us. We have discussion board, CK12 work, and that's it. Now to help you in between, there are the PowerPoints or Prezi lectures. This one is a Prezi lecture. And those are designed for you to get background information. It's as if I were lecturing to you in a classroom. I really tried to look at this week's CK12 work and match it up with the lecture. So you'll want to watch it. Last week, we went over some problems from the prior week that were tripping some people up. I go over some problems in this one, so that way it's already built in. So you'll see here you have the Prezi with no lecture, and then you have the Prezi with the lecture. So I can also state this as the non-annoying Prezi, the one where there's no lecture, and the annoying Prezi, where you have to listen to me tell terrible jokes about me eating cereal in my mid-20s. So there's that. Anywho, so let's click on the first part. Newton's laws of motion, the discussion board, as always, just a short video. Now, this one isn't the best video. I'll say that. The narrator is kind of terrible. Him and I might be related. Who knows? But it does a good job of explaining the 3 laws of motion in a concise way and in a shortened version. So I didn't want something that was going to go on for 10 or 12 minutes. This one is done in about 3 minutes, and you just have this one question to answer. How are catapults and trampolines examples of Newton's laws of motion? They talk about that directly in the video. You don't have to make some weird connection or go Google searching. They talk about it in the video. So just watch it once, maybe twice, and you'll be able to nail that question. And the follow-up to it is which of Newton's laws are associated with both of these items. You don't have to get super detailed. You could just say Newton's first law, Newton's second law, Newton's third law. I'm giving you 2 examples. I guarantee you they're both not the same one. So literally, if you just guess 2 of them, one of them is probably going to be right. It has to be right? The laws of averages there. But no, please do watch it so you can see how catapults and trampolines which are simple things that we've seen used. If you ever gotten like a food fight and you like fling mashed potatoes from a spoon, or if you've ever jumped on a trampoline or gone to one of those trampoline parks where those kids go bonkers in, like that is, it's, I don't know, it's like it's pure danger. Just never go to them. It's always dangerous. It's always sweaty, and it's not a good time. But those simple things that we see in life, like catapults, we see those every day, right? You have to worry about cows getting flung over the wall, in case there's any Monty Python fans out there. But no, so catapults and trampolines are just everyday things that followed Newton's laws of motion. So they're really important. And Newton had this great way of he had this phenomenal way of taking things that were very complicated and making them very simple, and then taking these simple things and then finding the beauty and the complex structure behind them. So he was someone absolutely to be admired. He ran, or was the president of the British Royal Society for a long time. Just a great human being, if you will, contributed a lot to the sciences. So that's your first part. Your second part is just this page that takes you to CK12. And so I already have it open here. So if you click this, you're going to be taken to our class. And you're going to see, here it is, week 11, Newton's laws of motion. And I'm giving you an early Christmas gift here, because if you hit that and you look at it, Newton's first law, second law, third law. That's it, and there isn't a quiz. I think the adaptive practice on these is more than enough to show me that you have comprehended the unit and the presentation, if you will. So I left a quiz off of this week's work. Do not worry about it. Just get through the adaptive practice, and you'll be all good. Now, each of these will go through, his laws and give you examples that you're also going to see within the PowerPoint that we're about to do, or the Prezi rather. I have this due date on here. It is arbitrary. You have until the end of the semester, which isn't that far away. Sorry for the finger wagging. That's not cool. But it's not that far away. So just please make sure you're keeping up with the CK12 work. I do not envision us having another week where I just say catch up on stuff. We'll pretty much be hitting new topics from here till the end of the semester. So you click on those, you know what to do. Newton's first law, you have your reading, which you should do because it'll back up what was said in the PowerPoint. You have real world examples, you have videos, you have these little almost like games you can do, and then you have the adaptive practice once you feel comfortable that you can answer questions about it. So you go through those, you'll do it for the first, second, and third law, and that's that. So now if we go back to our module, this one here, week 11 Prezi, no lecture, just takes you right to the presentation I'm about to do. And then the other one, that's the presentation I'm about to do. If you go to the other one, it'll take you right to this video. It's kind of weird. It's like, I don't know, I'm speaking to you from the future. I don't know. Let me stop making terrible jokes and let me get into our lecture. So I'm going to take a quick drink of water. Newton's laws of motion. So we have 3 laws. We're going to go over each of them, and our objective is just to identify and explain how Newton's laws of motion relate to the movement of objects. If you think about a baseball being hit, a bowling ball being rolled down the alley. Speaking of baseball, if you're talking about a baseball traveling at 80 miles an hour and Cody Bellinger reaches over the wall and pulls it back and stops its acceleration, we can thank Newton for being able to understand that. That's an amazing thing. And so it relates to everything we see on a daily basis. I apologize for that. But this relates to space travel, car accidents, skateboarding. Anything that is in motion obeys these laws. So there are 3 of them. Now, there's a little video here. You can watch it. It talks about Sir Isaac Newton. I think it is invaluable. But in order to keep the video short or this lecture short, I'm not going to click it. You can play it on your own, and that way this video doesn't run too long. But Sir Isaac Newton came up with 3 laws of motion. His first law states that an object that is at rest will stay at rest, and an object that may be in motion will stay in motion at a constant velocity, unless acted upon by an unbalanced force. We're going to talk about all of those. But this whole unit sort of relates around motion as regard to forces. So if I'm sitting here at rest, I'm going to stay at rest. Nothing's going to move me. Now, say if there's an earthquake and I got pushed to the side of my apartment here, then I'm going to be in motion, and I will stay in motion unless acted upon by an unbalanced force. His second law, force equals mass times acceleration. There is a wonderful little jingle that goes with this that we will talk about. And then we're also going to look at an example of a sumo wrestler fighting a baby and who would win and why. I think you know who would win, but we want to know why. Now, the third law. In this one, we've heard, this gets made almost into a cliche. Like, people use this for like revenge sometimes. But Newton's third law says for every action, there's an equal and opposite reaction. And so people have extrapolated that out to mean many different things. But in regards to motion, that this is just saying that in every action and motion, there's an equal and opposite reaction. This relates to car movement. If you're playing pool, you're using the third law of motion. So, hopping into the first law. If you haven't seen this video, oh my goodness, it is so cool. It's Felix Baumgartner jumping out of a weather balloon way up in the earth. You can see the curvature of the earth, which proves it's not flat. And he skydives all the way down. It's an incredible video. YouTube it, Felix Baumgartner. It'll be the first thing that comes up. So, the first law of motion, like we just said, an object at rest stays at rest, or an object in motion stays in motion at a constant velocity unless it's acted upon by an unbalanced force. Just stating our law. Now, so this is also called the law of inertia. So we need to know what inertia is. So it's the resistance an object has to a change in its state or motion or lack of motion. So me just sitting here, I'm just being a stump. I'm not doing anything except talking into the computer, which is weird enough. But say if someone came up and they just like lightly pushed on me, I'm not going anywhere because it's my resistance to movement. So inertia is your resistance to movement. Also, if you're moving, the change in motion, if you were to stop, is a change in inertia. So it is a property of matter to be in motion and to have inertia. So it is just the resistance an object has to change in its state of motion or lack of motion. So either it's going to change from being like not having any motion to having motion, or to having some sort of motion and then not. So you can see this picture here. So this truck was clearly carrying some huge hunk of stone in the back. And for some reason or another, he was cruising along. Say he was going 80 miles an hour, cruising along. At the same time, that stone slab in the back is going 80 miles an hour with him. If he slams on the brakes and has that negative acceleration like we saw last week, the stone doesn't. The stone keeps going. It is going to be thrust forward because it has the inertia of motion with it, to where it's going to keep going forward unless it's acted upon by an unbalanced force, which is now the stopped truck. So there we go. We're connecting some dots already. That's pretty cool. So what 3 safety devices help protect you from the law of inertia? And explain. So you can go through these videos and you can sort of see, but we're just going to talk about them. Think about driving in your car, because when you get in a car, if you're going 80 miles an hour, yeah, sure, your car is going 80 miles an hour, but so are you. You are in the car, which is going 80, so you're going 80 miles an hour too. Say if you get into an accident or you got to slam on the brakes, your car will slow down, but you're going to stay in motion. So the thing that stops you is your seatbelt. So if you're just braking really hard, that seatbelt locks in and holds you there and stops your inertia. If you get pushed back, so say, someone hits you from behind. If you're stopped and someone hits you from behind, your car is going to go forward, but you're not. So that headrest behind you that you sort of lean into or hit, if it's a hard enough collision, that stops your inertia. Furthermore, say if you are unfortunate enough to get into an accident and you hit head like straight on, if you're going forward, that airbag that deploys, that stops you, that once again halts your motion. And so it is a part of protecting you from the law of inertia. So those are 3 examples. So we're going to hop through these next ones. You can absolutely watch those videos, and I recommend that you do for deeper understanding. All right. So if you think of a golf ball, if you've ever been to the driving range or anything like that, unless acted upon, when it's on the tee, like so when you set it up to, tee off, you're in the tee box, unless it's acted upon by an unbalanced force, which would be you swinging a club, that golf ball will stay there on the tee forever. Now, you could be like, well, what if it's windy and it gets knocked off? That's a force. Wind is a force. That's motion. That's cool. But that's a great question. I'm glad you asked it. Once again, bad jokes. I'm sorry. But what if the golf ball is hit? So say I wind up and wham, I hit the golf ball. Clearly, it doesn't go on forever. It comes back down. But what's the force acting on it there? So once I hit that golf ball and it's airborne, if it wasn't being acted upon by an unbalanced force, it would just sail on forever. But we have gravity, which is going to be pulling it towards the center of the earth. And we also have air, which will provide resistance and friction. That's something we're going to get into a bunch right now, is friction. And so air, believe it or not, is considered a fluid because it is a moving medium. And so that fluid friction is what stops the ball. So the fluid friction, along with gravity, will bring it back down to the ground in that nice sort of parabolic arc. Otherwise, it go on forever. So let's recap the first law. So why, when we observe everyday objects that are in motion, slowing down and becoming motionless, seemingly without a force? We know that there's a force. There's the force of friction. There's the force of gravity. Occasionally, it is just a force that we cannot see. If a car drives head first or front first into like a brick wall, we can see the forces in action. The car going forward is a force, and that wall that ain't going anywhere is a force. But if we hit that golf ball, we can't see gravity. We can't see, air resistance and fluid friction. Therefore, it could just be a force that you cannot see. So if you look at this big box, if any of you played football, where you had like the tackling sleds you had to push, or if you've ever like pushed like a big box or anything across like the carpet, you feel like that resistance to the motion. So that resistance is inertia. But then if you have an unbalanced force, you can start to move that box. But say if I just pushed it, and think about this way, if I had a carpet or if I had ice, if I had a box that was on ice and I pushed it, it would keep sliding for a while because there's not much friction between the ice and the box. But with carpet, it's a much more rough substance, and it has a lot of friction to it. So as you push it across the carpet, it would slow down faster because the force of friction is that much higher. I need to take another need to take another drink of water before we get into the second law. So let's watch really quick the tablecloth trick, because there's some questions after here that'll be important for us. And this was part of Mythbusters, which was really cool. And I'll stop it after a little while. So I pause right there because you said something very important. If the inertia is greater than the friction, it ain't going to go anywhere. It's going to stay put. So when they pull that tablecloth off and the bottle doesn't go anywhere, it's because the inertia of the bottle was greater than the friction between the bottle and the tablecloth. All right, so we're not going to watch the other fabrics part. But we want to talk about what we learned just from watching that quick little video. And it's like a trick we've always seen. I first saw that trick when I watched Ghostbusters for the first time when I was a kid. Bill Murray, who played Peter Venkman, pulls a tablecloth off the table, and everything falls except for this pot of flowers. And he says, the flowers are still standing. It was just a great moment in my life. Sparked me into science right away. And now I know, looking back, I could say, okay, Peter Venkman, you may be a wonderful Ghostbuster, but the reason for those flowers still being there is because the inertia of that flower pot was greater than the friction of that tablecloth. And he would probably hire me on as a Ghostbuster and I'd become famous, but that's another topic for another day. So what did we learn from that little video? Does the location of the tablecloth affect the experiment? Absolutely it did. But the reason was because, as you saw, when he was pulling it and it was draped over, it had friction between that first sort of dimension of the table and then the long dimension of the table. So that added friction became too much for the inertia of the bottle and it fell over. So we're not going to worry about the fabric of the experiment. We need to just sort of understand the motion. But how does this experiment relate to Newton's laws of motion? So that bottle is going to stay where it is unless we pull on it. We're an unbalanced force when we're pulling on it. But if the force of friction is so low that it cannot overcome the inertia, it would stay right where it was. All right, so you can always try this at home. You can slide a book across the table and it's going to slide to a rest. And the reason that it does is the presence of those invisible forces of gravity and friction. Otherwise, it would just go on forever or until it fell off of the tabletop. There you go. So our second law, Newton's second law of motion. So the net force of an object is equal to the product of its mass and acceleration, which is saying that the force of something is the mass multiplied by the acceleration. So I told you there's a great jingle that goes along with this. I learned it in my college physics class, and it's one of those that got lodged in my head and it hasn't left since. And it just says, hooray, hooray, F equals ma. So force equals mass times acceleration. It's a way to always remember it. Now, you don't need to remember it because you can always refer back to this presentation. Maybe you want to remember it so you don't have to go back to this presentation. I would understand that. So when mass is in kilograms and acceleration is in meters per second, the unit of force that is coming out of that is called the Newton. And you can understand why they named a unit of force a Newton because of some of these laws. Now, you don't need to know that it's meters per second and kilograms. All you need to know is that we refer to it as a Newton in terms of force. So 1 Newton is equal to the force required to to accelerate 1 kilogram of mass at 1 meter per second. Like I said, we don't need to memorize that or have that down, but I owe you the explanation as a teacher. So there we go. 1 kilogram per meter per second is equal to 1 Newton. Just way easier to say newtons. So if we were in class, normally this would be like where we sort of talk amongst one another. But the question here is, if two objects have the same acceleration, but one was twice the size of the other, which object has the greater force? This is where force equals mass times acceleration comes into play. So if we're looking at which one is going to have the greater force, we have to look at those two variables, mass and acceleration. They're telling us here acceleration is going to stay the same. But now we're looking at mass. Remember I was telling you about a sumo wrestler fighting a baby? Well, it's about to get real. So if you look at this picture here, we see a sumo wrestler versus a very small child. It does not take much thinking of who on earth would win this battle if they just charge towards each other. So if they charge towards each other with the same acceleration, which one's going to have the greater force? You already know it's going to be the sumo guy. But why? And the reason is because of the mass. So if force is equal to mass times acceleration, and their accelerations are the same, then the greater force is going to be had by the object with the greater mass, which is the older gentleman in the diaper as opposed to the little kid in the diaper. I'm sure it has names. I do not mean to offend. It's just, I don't know, bad jokes. And who knows how many people are watching the video to this point anyway. So let's just have fun with it. So there we go. So the sumo wrestler wins because he has the greater mass and therefore can produce the greater force. But that should also show you. You ever seen like some of those videos where like they're like, not hurricane, but like maybe hurricane. Like a tornado came through and this twig went through a tree. And you're thinking like, how is that even possible? Because the tree has much more mass than like a twig or a stick, but that tree would be stationary. So it would not have acceleration. That twig whipping around from the tornado or hurricane has acceleration. So now you'd almost be flipping those around, and that's how like a twig can go through a tree during a hurricane because of the acceleration, which would lead to a greater force. Okay, so you may see some questions like this in your adaptive practice when you're talking about the second law of motion, and they may say something like, how much force is needed to accelerate a 1,400 kilogram car 2 meters per second per second? It seems very confusing, but we just have to remember, hooray, hooray, F equals ma. Force equals mass times acceleration. We're looking for force, we have acceleration, and we have mass. Therefore, we just multiply those two together. For a solution, write the formula. F equals mass times acceleration, so force is mass times acceleration. Fill in the numbers that they give us. Force is equal to the mass, which is 1,400 kilograms, times the acceleration, which is 2 meters per second squared, or 2 meters per second per second. And that's just multiplying. If you want, boom, get rid of those units. You know any unit of force is going to be in Newton. So 2 times 1,400 is going to give us 2,800 newtons. Easy as that. I say that because I've seen this a million times and I've done it a million times. If you're confused by it, it just means you're totally normal. If you have questions, ask them, please. I would love to answer them. So let's check our understanding. If you look at some of these, so what acceleration will result when a 12 Newton net force applied to a 3 kilogram object or a 6 kilogram object? So we just once again want to use that formula. If F equals mass times acceleration, well, we know from algebra we can move those around. If we're looking for acceleration, we just have to divide force by mass. So they're telling us the things we know here. 12 newtons, which is our force, divided by our mass, which is 3 kilograms, would mean that the acceleration is 4 meters per second squared. If it was a 6 kilogram object, we would take that same 12 newtons and divide it by 6 kilograms, and therefore we get 2 meters per second squared. So if a net force of 16 newtons causes a mass to accelerate at a rate of 5 meters per second squared, determine the mass. Okay, we're once again just moving that equation around. If F equals ma, and they're asking us to determine the mass, we just have to take the force divided by the acceleration. So the force being 16 newtons divided by 5 meters per second, 3.2 kilograms. That's it. So the only two things we're doing here is multiplication and division. Now, like I said, I've done these hundreds of times, so it comes second nature to me. If you're having questions or if it's frustrating you, just ask me. We'll go through them together. So how much force is needed to accelerate a 66 kilogram skier 1 meter per second squared? Well, this one, we don't need to move the equation around. It's just they're looking for force, so we take mass times acceleration. So it's 66 kilograms times 1 meter per second squared. 66 times 1 gives us 66. Our unit of force is in newtons. So the next question, once again, they're asking for force. So all I have to do is multiply the kilograms, so the mass, times the acceleration. And so it says, what is the force on a 1,000 kilogram elevator that is falling freely at 9.8 meters per second squared? So we don't need to know it for any specific reason, but that 9 meters or 9.8 meters per second squared, that is the force due to gravity. So they say it's falling freely. So if it's falling freely, everything that's falling freely is going to fall at 9.8 meters per second squared. That is the acceleration of gravity. So you take 1,000 times 9.8, and we get 9,800 newtons. That's it. Not too terrible. All right, so let's go to the third law, our reaction and action law. So his third law of motion, him being Newton, says that for every action, there's an equal and opposite reaction. He's not talking about behavior. He's not talking about getting upset. He's talking about motion. So we have our action and our reaction forces. And you can see by the arrows and how they're sort of set up here, they're equal in length, but in opposite direction. So this comes in very useful when they're talking about space travel. So when that rocket blasts off, the chemical reaction that creates combustion, that releases all the energy out of the jet engines. The action is pushing down towards the Earth, but since there has to be an equal and opposite reaction, means that if it's forcing down towards the Earth, it's also going to be forcing away from the Earth. And in this case, our acceleration is going to increase, which gets these astronauts into space. So there's a video you can watch if you like. I put it on there. It will help you understand what I was talking about there, but this video is already running long, so I want to try to keep going. I just cut out the bad jokes. It'd probably be like 6 minutes long. But so if we look at these two pictures and we want to explain the action and reaction that's going on here, the first one is a gentleman who is skateboarding. And so we can see here what he's going to do is he's going to push off with his right foot there. So that action is pushing towards so it's pushing behind him as he pushes his foot off. And the resulting action, so the reaction, is going to be him going forward on the skateboard. But he is only going forward because he pushed back in the opposite direction. So for every action, there's an equal and opposite reaction. So whatever force he pushes off with going backwards is the force he's going to hit going forward. On the right, we have this dude jumping off of a boat. And so he's going to be falling towards Earth. So he's going to be falling at 9.8 meters per second squared, which is the acceleration due to gravity. And that water is waiting there to push right back up on him. So as soon as he hits the water, there's your equal and opposite reaction. So he's going down towards the water, and then there's going to be the force pushing him back up once he hits that body of water, which will not feel good. So that's it. Those are the 3 laws. So let me hop out, go back to our course here. You have the 4 sections. You have everything you need. Everything is unlocked and ready to go. If you have any question whatsoever, message me on Canvas, message me on Remind, send me a regular email. We will have our Zoom tomorrow from 6 to 6. Oh, wait. I'm saying that, but you're going to be watching this after that. So forget what I just said. Let me end it there. Thank you for tuning in, and always ask questions. Have a good week.